Module 7, Describing Chemical Reactions. Atomic mass. Now that we've gone over the three major types of chemical reactions, we can discuss how to count atoms and molecules. Counting atoms and molecules is not like using a teeny tiny tweezer and counting them like a pile of beads. Remember, scientists have never actually been able to see an atom. So how can we count them? Well, with the information we know about elements, we are able to measure the mass of a sample and then figure out the types of atoms or molecules in that sample. Armed with that information, we can determine how many atoms or molecules there are. It's time to pull out your periodic table of the elements again. Believe it or not, this amazing chart can tell us even more information about elements than you have already learned. Within each box, there is the atomic symbol. Now notice the two numbers there, one on top and one below. We have already discussed that the symbol is an abbreviation of either the Latin or English name for the element. The number above that symbol is called the atomic number. It tells us how many protons that atom has in its nucleus. We've already talked a bit about that in an earlier module. So if you start with hydrogen and follow the chart from left to right, row by row, you can see that the atomic numbers increase one by one. So the periodic table is set up in order of increasing proton number. Isn't it fascinating that the elements we've found in our world exist without any proton number gaps? Now the number below the atomic symbol is called the atomic mass. It tells us how heavy the atom is. Of course, the greater that atomic mass number, then the heavier that atom's mass. Notice on the table how the atomic mass also increases as you increase atomic number. Well, there are no units shown in the boxes. What are the units for atomic mass? You can imagine they have to be extremely small units. After all, we know that one atom of carbon cannot be 12.0 kilograms or grams or even milligrams. That's just too giant for a single atom, isn't it? The units for atomic mass are called atomic mass units. Isn't that convenient? This unit is abbreviated as AMU, and it is a mass unit for chemists to identify the mass of atoms. It measures a teeny tiny amount because atoms have teeny tiny masses. But that's a good thing because the atomic mass units for atoms are nice numbers to use. They don't necessarily have to be shown with scientific notation, with most masses being in the ones, tens, or hundreds place. We do have a relationship between atomic mass units and grams, though. This will give you a better understanding of indeed how small these units are. 1.00 AMU is equal to 1.66 times 10 to the negative 24 grams. This is an important relationship to have, and you will be given it whenever you need it. But you need to understand that this relationship isn't an exact one. It has significant figures. So if you utilize this relationship in a conversion, you need to remember to consider that it has three significant figures. Now think about exactly what this relationship is telling us. A gram is about the mass of a paperclip. So a single atomic mass unit is 1.66 times 10 to the negative 24 of that paperclip. It's a trillion trillionths of the mass of that paperclip. That's tiny. So although you don't see scientific notation when you compare the masses of atoms to each other, you will be using it when you do calculations that have to use grams. Let's look at an example together. What is the mass of one nitrogen atom in grams, given that 1.00 AMU equals 1.66 times 10 to the negative 24 grams? We first need to look at the periodic table to know how many atomic mass units a single atom of nitrogen has. The table shows us that it has a mass of 14.0 AMU. So we just need to do a conversion problem. So what do we have? 14.0 AMU. Place that number over 1. What's the relationship between the units we have and the units we want? 1.00 AMU equals 1.66 times 10 to the negative 24 grams. Set that relationship up as a fraction so that the units we don't want cancel out. Now multiply through, and we get 2.32 times 10 to the negative 23 grams. Our answer has three significant figures like both of our given units, so we are good.